All right, so now let's actually do an example for mathematical induction. So we want to show that for all natural numbers n, the sum from 0 up through n, so 0 plus 1 plus 2 all the way up through n, that's going to be equal to n times n plus 1 divided by 2. And so first of all, let's kind of talk about like what even is like a predicate. What are we even trying to prove? And so a predicate is a mathematical statement that's either true or false. And so what we want to show is we want to show that for all k, we want to show p of k. And p of k is a claim. The predicate for the kth integer is that 0, the sum from 0 to k, so 0 plus 1 plus 2 plus dot 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 plus all the way up through k. It's a claim that this sum is equal to k times k plus 1 divided by 2. So let's talk about doing this on like a specific example. So if we do k is equal to 0, for example, then p of 0 is the claim that when we add 0 plus 1 plus dot 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 all the way up through k, so when we add, the first integers all the way through 0, we get back 0 times 0 plus 1 divided by 2. However, the left-hand side of our predicate, when we plug in 0, if we add up all the integers until we hit 0, is just 0. So the left-hand side is just 0. And then it's a claim, so I'm going to put a question mark on top of the equality sign. It's a claim that we have to show that this is equal to 0 substituted into the right-hand side of our predicate. So that's going to be equal to 0. The claim is that that's going to be equal to 0 times 0 plus 1 divided by 2. But if we do 0 times 0 plus 1 divided by 2, so 0 times 1 divided by 2, this is just equal to 0, right? So this is just equal to 0. And so then the left-hand side is equal to 0, the right-hand side is equal to 0, and so they are equal to each other, and so this claim is in fact true. So the predicate is true for k is equal to 0. Let's do kind of a bigger example. Let's maybe do k is equal to 3, just to get the concept down. So p of 3, the predicate on the integer 3, or the natural number 3, is that we're going to add all of the numbers starting from 0 up through 3. So we're going to do 0 plus 1 plus 2 plus 3. And we want to know, question mark, is this equal to when we plug in 3 into the right-hand side? So if we plug in 3, we're going to get 3 times 3 plus 1 divided by 2. And so now let's check to see if these are equal. So the left-hand side, when we add all these together, 3 plus 2 plus 1 plus 0, we're going to get 6. And so then for the right-hand side, we also want to get 6. So let's see if that's what we got. So 3 plus 1 is 4, so the top is going to be 3 times 4 divided by 2. 3 times 4 is 12. So this is 12 divided by 2. 12 divided by 2 is in fact equal to 6. And so we see that the left-hand side of the predicate is equal to the right-hand side of the predicate, and so then the predicate is in fact true for k is equal to 3. Sweet. So it kind of looks like that our predicate is true for like a couple of different base cases. K is equal to 3, k is equal to 0. So now let's check to see if it's true in general. And so let's do a proof of that. So let's write down the proof. So these are the constituents of any proof by induction. So we always have a base case, inductive hypothesis, and induction step. And so let's talk about these. So your base case, you're just going to write down in this case, our base case is n is equal to 0, so we're going to say n is equal to 0. And so we're going to write down the left-hand side of our predicate. And remember what we said was that when we add up, all of the integers or the natural numbers up until 0, we just get 0. So we're going to have 0 is equal to, and then the right-hand side, we're just going to plug in 0. So we're going to get 0 times 0 plus 1 divided by 2, and that is equal to 0. Nice. And then the inductive hypothesis is that we're going to assume that our statement or our predicate is true for some k value greater than or equal to our base case. So greater than or equal to 0. So what we're going to write is we're going to say assume that P of k is true for some k greater than or equal to 0. And then what I like to write is I like to rewrite the predicate. So i.e. assume 1 plus 2, or excuse me, 0 plus 1 plus 2 plus ... plus k is equal to k times k plus 1 divided by 2. So that's what we're going to assume. And then we're going to use this inductive hypothesis to show that the predicate is also true for the k plus first value as well. So let's do that. And so normally how the induction step goes is you just say consider k plus 1 or consider p sub k plus 1. The predicate on the k plus first value. So let's just write down consider k plus 1. And then now what we're going to do, usually what we're going to do is we're going to write down one of the sides of the predicate. So either the left-hand side or the right-hand side, and then we're going to end up on the other side. And so let's write down 0 plus 1 plus 2 plus ... plus k plus 1. So this is the left-hand side of the predicate on k plus 1. And what we want to end up with eventually is we want to eventually end up with, our right-hand side of the predicate where we substitute in k plus 1. So we want to eventually end up with k plus 1 times k plus 1, which is k plus 2, divided by 2. But we can't write this down immediately. So this is not a true statement. We haven't proven it yet. And so what we're going to do is we're going to move this off to the side, and then we're going to eventually end up there. So we want this to be equal eventually, and then what we need to do is we need to fill in the steps that get us there. And so let's talk about how to fill in the steps to get us there. So another thing to note is that we need to use the inductive hypothesis. If we're not using the inductive hypothesis, then we're probably not doing induction. And so let's talk about how to use the inductive hypothesis. So we wrote down the sum from 0 to k plus 1. And if we kind of look at it, we can see that, this right here, this first bit is the left-hand side of the predicate in the inductive hypothesis. And so using the inductive hypothesis, that means that that whole first bit is equal to k times k plus 1 divided by 2. Sweet. And then now if we need, so this is equal, so we need to write down the second bit as well. So plus k plus 1, k plus 1. And then again, substituting in k times k plus 1 divided by 2 for this first bit came from the inductive hypothesis, right? We know that that's true from the inductive hypothesis. Okay, so now we want to add these two things together. And normally when we add two things together, we need to have them or excuse me, when we add two fractions together, they need to have the same denominator. So we need to put a 2 on the bottom of here. So let's just multiply it by 2 on the top and the bottom to get the same denominator. So this is going to be k plus 1 divided by 2 plus 2k plus 1 divided by 2. Great. And so then now let's actually add those together. So then that is going to be equal to k times k plus 1 plus 2 times k plus 1 divided by 2. And so all I did was I just added these two fractions together, so this fraction and this fraction. And when you add fractions with the same denominator, you just add the numerators. Great. So now let's factor out the k plus 1 because it's in both terms of our numerator. So let's factor it out. And when we factor it out, we get k plus 1. And then what we're left over with is the k plus 2. So this is going to be k plus 2 divided by 2. And that's where we wanted to end up. So nice. We can kind of get rid of this. And that's exactly where we wanted to end up. So now we're basically done. So what we showed, so let's kind of run through this again. What we showed was that our predicate is true for some base case. So it's true for n is equal to 0. And then assuming that the predicate is true for some k value, and using that that is in fact true, we can show that the predicate is true for the next k value as well. So we just showed that the sum from 0 all the way up to k plus 1 is equal to k plus 1 times k plus 2 divided by 2. And so those two pieces together tell us that the predicate is true for all natural numbers n. So what we can conclude is, therefore, P of n is true for all n greater than or equal to 0.